Hello everyone, welcome to this session. Before starting this session, let us spend a couple of minutes on what we studied till now. If you kindly recall, we started with fluid dynamics. There we derived Euler's equation, then we derived Bernoulli's equation, then we studied about the applications of Bernoulli's equation. If you kindly recall, we discussed about Venturi meter, we discussed about orifice meter, we discussed about pitot tube, pitot static tube. From then on, we move on to this orifice and mouthpieces. We studied about different types of orifices, mouthpieces, and we derived the discharge equation both for the orifice and mouthpiece. We compared or we differentiate between orifice and mouthpiece. Of course, along with couple of problems. Then we moved on to this notches and wears. We differentiated between the orifice and a notch, and also the mouthpiece and the wear, notch and a orifice. Then we discussed about the different types of notches, different types of wears. Then we derived equation for a rectangular notch, triangular notch, trapezoidal notch, and also stipulated notch. We also discussed about step notch, and finally sutro notch or proportional wear. We also discussed about the advantages of this V notch over other notches. These were the couple of topics which we discussed in module 3 and module 4. Let us move on to this module 5, which is again very important for a civil engineer. If you take out your syllabus and if you observe the syllabus, the first and the second chapter talks about the basics. Okay, you talk about fluid statics, then we moved on to fluid kinematics, then fluid dynamics. From then onwards, we started moving towards the practical problems what you are going to encounter once you go out of the portals of your college. Okay, so among that, if you kindly recall, I said this notches and wears and this orifice and mouthpieces are part of civil engineer's life. So similar to that, this pipes is also, flow through pipes is also very important for a civil engineer. Let us study this flow through pipes in detail. Actually, couple of things which we already discussed under fluid dynamics. Maybe there may be a couple of items which are repetitive. Anyway, it is good. It will be a recap for you to. With these basics, let us start this module. Basically, whenever we talk about flow or fluid flow, there are two types. One is a pipe flow, the other one is a open channel flow. This open channel flow you are going to study in the next semester. Now, this third semester or this fluid mechanics is completely devoted to this pipe flow. Then how do you define this pipe flow? So, pipe flow refers to full water flow in a closed conduit. This is very important. Okay. Now, whenever I am talking about a pipe flow, this refers to a closed conduit or a circular cross section under certain pressure gradient. This is a basic definition of a pipe flow. Now, what are the characteristics, or how do you define a pipe flow? Now, when I want to define a pipe flow, okay, it can be described by, now the pipe has a certain cross section A. Now, this pipe is placed with reference to datum at certain level, that we call it as what is known as elevation. Then we talk about what is known as pressure. Okay, remember. So, once the fluid flow starts flowing through the pipe, the pressure varies from point to point. If you kindly recall, in fluid dynamics, when we discussed about this Bernoulli's equation, so Bernoulli's equation states that the total energy all along the reach remains the same. So, in case of a ideal fluid, since we assume that a fluid is ideal, the total energy from section to section remains same. But if you kindly recall, when we are talking about real fluids, okay, the total energy at section 1 is not equal to the total energy at section 2. In that case, in order to make total energy at section 1 is equal to total energy at section 2, for the total energy equation at section 2, we added the term called head loss. Okay. Now, the same things we are going to introduce in this chapter. Now, finally, so we need to calculate how much quantity of water is flowing. Okay. For that, we use that continuity equation Q is equal to A into V. So, depending on the unknown, we use this Q is equal to A into V or V is equal to Q divided by A. I showed couple of figures here. Okay, the first one is a pipe flow in a water supply. The second one is look at the velocity at which the water is emerging from the dam, and in case of a irrigation, okay, this is the pipe flow in case of a irrigation pipe. Then here, okay, there is a river flowing. Over this river, there is a bridge. On this bridge, there is a pipe. Okay, this pipe carries a fluid. It may need not be water. So, from this bank to that bank, and this is a typical setup for a centrifugal pump or a turbine. Okay. Now, these are the pipes that carry water from the dam or carry water from the sump to the overhead tank. Let us go back to this fluid dynamics. Kindly recall, total energy consists of three types of energies. One is kinetic energy, the second one is potential energy, the third one is pressure energy. So, what is kinetic energy? V square by 2G. What is potential energy? Potential energy is nothing but the datum energy. It is the energy with respect to which we are measuring the with reference to an arbitrary datum. Pressure energy, so P is equal to gamma into H. I am looking for that pressure head, therefore H is equal to P divided by gamma. Again I repeat, these are the things which we studied in fluid dynamics. Okay. This is a figure what we put over there in fluid dynamics. Now, if you look at this, now this is your potential energy, this is your pressure energy, this is your kinetic energy. Similarly, when you come to this point, so you have this datum energy, pressure energy and kinetic energy. Just now I said, okay, now for a ideal real fluid, the total energy at point 1 is not equal to the total energy at point 2. In other words, if I draw a horizontal line here at section 1, okay, the total energy at point 2 is also at the same level. But here in this case, so this is not the case. So, in order to make this energy is equal to this energy, I need to add a term called HL, which is nothing but the head loss. Now, this whole chapter is devoted to this head loss. The first question is, what is this head loss? Why it occurs in pipes? Remember, kindly go back to your first chapter where we discussed about viscosity. What is viscosity? It is the resistance offered by the flowing fluid. I repeat, viscosity is the property by virtue of which it offers resistance to the flow. Okay. If you kindly recall, when I was talking about Bernoulli's equation, I said if you take typical two types of pipes, cast iron pipe and PVC pipe. If you take the cast iron pipe, if you hold your finger inside the pipe, usually the inside surface of the pipe is not smooth in case of cast iron pipe. On the other hand, if you take a PVC pipe, if you hold your finger inside the pipe, the inside surface roughness is almost nil in case of PVC pipe. Since in case of a cast iron pipe, the surface roughness is very high, so whenever a fluid is flowing in such type of pipe, there is always a resistance. Due to this resistance, there is a drop in pressure from section to section. That is why if you take any water supply project or irrigation project, nowadays most of the time these PVC pipes are replacing this traditional cast iron pipe or mild steel pipes. Okay. Now, what is the takeaway from this figure? Now, from this point to this point, there is a drop in pressure. So, why this drop in pressure? That is because of the surface roughness. Okay. There are different types of reasons. Okay. One reason is the pipe friction. Okay. Let us see what are the other types of things that decrease this head loss in couple of slides to go. This is what I just now said. The total energy at any point is given by kinetic energy, pressure energy plus datum energy. Okay. Now, for a ideal fluid, P1 by gamma V1 square by 2g plus Z1, that must be equal to P2 by gamma plus V2 square by 2g plus Z2 for a ideal fluid. Now, for a real fluid, okay, on the right hand side, in order to make this LHS is equal to RHS, we need to add this HL. Now, this equation holds good for a real fluid. Now, with that basics, let us start the business. Okay. So, remember, the chapter or the module talks about flow through pipes. So, whenever you want to calculate the discharge flowing in the pipe, you need to account for all these losses. Okay. The question is, sir, why do I need these losses? For example, I will give a simple example. If you want to lift water from the sump to a 10-story building, suppose if you use a cast iron pipe, and if the capacity of the pump you are going to use is very small, can you expect delivery there at the top of the 10th floor? No chance. Why? In that case, your losses are more than the pressure developed inside the pump. So, that is why we need to account for these losses. That is why whenever I am talking about flow through pipes, these losses, major loss and minor loss, what I mentioned in this slide are very, very important. Let us see. So, basic idea behind this module is how to calculate this major loss, what are the different types of minor losses, and how to calculate these minor losses with different equations. That is the whole idea behind this module. Along with, we talk about pipes in series, pipes in parallel, and we do talk about what is known as pipe networks. That probably at the fag end of this chapter we are going to discuss about that. Okay. So, in general, when a fluid is flowing through a pipe, the fluid experiences some resistance due to which some of the energy of fluid is lost. This is what I mentioned just now. Now, these energy losses are broadly classified into two types. One is a major loss, the other one is minor loss. When I am talking about the major loss, it is due to frictional loss. That is why most of the time it is also called friction loss. Rather than calling it as a major loss, we call it as what is known as a friction loss. Now, come to minor loss. Loss due to change of the velocity of the flowing fluid in the magnitude or in the direction. I repeat, loss due to change of velocity of the flowing fluid. When you are going to encounter this change in velocity, suppose I consider a pipe diameter of say 10 centimeter. Suddenly I change the diameter to say 15 centimeter. Remember, water is flowing in 10 centimeter diameter pipe, and suddenly you change it to 15 centimeter diameter pipe. Maybe after some length, maybe again if you reduce that to say 5 centimeter pipe, naturally there will be changes in the velocity from pipe 1, pipe 2, pipe 3. So, whenever we have this type of problems, there is a certain amount of pressure drop. This is one type of case. Second type of minor loss is, suppose you are taking in this direction, you want to change the direction of flow, you want to put a bend. Okay. So, whenever you put a bend, naturally there will be some loss. Okay. So, that is another point where we encounter this loss. Then the third one is, suppose if there is an obstruction in the flow field, there is a pipe. So, inside the pipe, suppose there is an obstruction. In that case, the obstruction acts as an aerofoil and the fluid flows around the obstruction. In that case also there is certain amount of loss. All these type of losses constitute what is known as minor loss. So, that is what I presented in the next slide. Head loss due to friction. Energy lost through friction in the length of pipe is commonly termed as major loss. This is the loss of head due to pipe friction and to the viscous dissipation in flowing water. Now, Several studies have been found that the resistance to flow in a pipe is, this is very important, the same things I am going to talk when I start deriving an equation for this major loss. One is, this resistance is independent of pressure under which the water flows, and the resistance is linearly proportional to the pipe length, and it is inversely proportional to some water power of the pipe diameter d, and this resistance is proportional to some power of the mean velocity v, and it is related to the roughness of the pipe if the flow is turbulent. For the time being, let us not bother about this color letters words what I used here. Why I'm telling this is, as we progress, you yourself will be the master, and you will be at the end of the chapter, you yourself will be in a position to say that this resistance is depending on or it is independent of so such and such a factor. Okay. Let us start with the first one, major loss. There are several formulae to calculate this major loss. Among these, the most popular ones I mentioned here. One is Darcy-Weisbach formula, the second one is Aizen-Williams formula, the third one is Manning's formula, fourth one is Chase's formula, and the fifth one is Strickler formula. Okay. Among this, in the syllabus, they mentioned about Darcy-Weisbach formula, so that's why my talk for the next couple of minutes is restricted only to Darcy-Weisbach formula. You are going to study this Aizen-Williams formula, Manning's formula, Chase's formula in the 5th semester, or some of the formulae you are going to study in the next semester. Alright. For the time being, let us talk about this Darcy-Weisbach formula for this major loss. This is important. The resistance to flow in a pipe is a function of the one what I presented here. I want all of you to concentrate on this, because this is the one which I am going to use in the derivation. One is pipe length, the next variable is the diameter, the next one is the velocity, then the properties of the fluid, and basically the properties of the fluid also influence, the roughness of the pipe also influences the resistance. So all these factors we are going to take into consideration while deriving an equation for this resistance. Let us see how to derive an equation for this resistance. Remember, this is Darcy-Weisbach equation. Okay. What it says, the head loss due to friction is equal to 4f Lv square divided by 2gd. One of the important formula which you should not forget throughout your lifetime. I repeat, head loss due to friction is equal to 4f Lv square divided by 2gd. We will see one by one terms probably at the end of this derivation. In order to derive an equation for this head loss due to friction, I consider a horizontal pipe carrying a fluid. I repeat, in order to derive an equation for this head loss due to friction, consider a horizontal pipe carrying a fluid Q. Okay. So on this pipeline, I consider two sections, section 1-1, section 2-2. Now kindly remember, I'm sorry, kindly note down, the length between the section 1-1 and section 2-2 is L, or section 1-1 and section 2-2 are separated by a distance L. So what is L? The length between two sections 1-1 and 2-2. Very important. Then I defined another couple of terms here. One is P1, intensity of pressure at section 1-1. Similarly, at section 2-2, this intensity of pressure is given by P2. Now, what is this section 1-1 and section 2-2? This is called the control volume. What is this control volume? Control volume you studied under fluid kinematics. It is a fixed volume in space. Okay. Now, control volume consists of So, the area between this section 11 and section 22. Okay. So, let us define this P1 intensity of pressure at section 11. Similarly, at section 11 the velocity of flow is given by V1. L is the length of the pipe between 11 and 22. We define the diameter of the pipe as D, and for the first time we introduce what is known as this frictional resistance per unit wetted area per unit velocity. Remember, right now we are talking about the frictional loss. Okay. So, all along the perimeter, okay, with which the fluid is in contact, there is a resistance. That is what I mentioned here. I represent this as F1. So, F1 is equal to frictional resistance per unit wetted area per unit velocity. My sincere request to you is, whenever you are defining this term, you must be very careful. I expect every one of you to write this complete, what this F1 represents. Then we define this HF. HF is equal to head loss due to friction. Okay. These are the definitions. Then similarly, if we come to section 22, we define this P2, the intensity of pressure at section 22, and V2, the velocity of flow at 22. Having defined these terms, what is the next question? Next step, applying Bernoulli's equation between section 11 and section 22. Write the Bernoulli's equation. Bernoulli's equation, or total energy at 1 is given by P1 by gamma plus V1 square by 2G plus Z1. Come to section 2, it is P2 by gamma plus V2 square by 2G plus Z2. Now remember, in this case there is what is called as a friction loss. Do not forget to put this HF. Okay. Kindly recall, the pipe is horizontal, therefore my Z1 is equal to Z2. Datum energy at section 1 is equal to datum energy at Z2. So, Z1 is equal to Z2, therefore your Z1 and Z2 gets cancelled. Then there is another assumption I made at the beginning. What is that assumption? The flow is uniform. Okay. How do you define uniform flow? The various physical parameters such as velocity, depth, density, temperature do not change along the reach. From starting point to the ending point, these parameters, they remain unchanged. That type of flow we call it as what is known as uniform flow. Since we assume that the flow is uniform, the velocity at section 1 is equal to velocity at section 2. Okay. So, since horizontal pipe, my Z1 is equal to Z2. In this equation, Z1 and Z2 gets cancelled. Since it is a uniform flow, so whatever the velocity you are observing at section 1, the same velocity you are observing at section 2. Therefore, V1 is equal to V2. Therefore, this term also gets cancelled. So, what you will left with this P1 by gamma on the left hand side, that is equal to P2 by gamma plus HF. So, kindly rearrange this equation. I am looking for an equation of this HF. So, HF is equal to P2 by gamma minus P1 by gamma. All right. I think it is here it is P1 by gamma minus P2 by gamma. Kindly make a correction here. If you keep this HF this side, then it will be equal to, you are pushing this P2 by gamma to the other side, therefore this becomes P1 by gamma minus P2 by gamma. Again I repeat, kindly make a correction, this is P1 by gamma minus P2 by gamma. But what is HF? HF is the head loss due to friction, and hence the intensity of pressure will be reduced in the direction of flow by frictional resistance. That is what we saw in the figure. If you introduce a piezometer at section 1, introduce a piezometer at section 2, okay, the piezometric height at section 1 is not equal to the piezometric height at section 2. So, we know that that is due to this frictional resistance. That is what I mentioned in this line. Now, the frictional force, which is always opposite to the direction of flow, is given by, I represent that frictional force as capital F1. So, F1 is equal to frictional resistance per unit wetted area per unit velocity. This we defined as small f1 into wetted area into velocity square. Okay. Now, this one capital F1 is equal to, this we represented as small f1 into wetted area. Remember, I said whenever water is flowing in a pipe, this flows all along the perimeter. Therefore, when I am talking about a wetted area, it is nothing but my perimeter over what length? The length of the pipe is under consideration from section 1 to section 2 is L. Therefore, in this case, in place of wetted area, rather than writing this pi d square by 4, okay, so please write that this pi d L. What is pi d? Pi d is the perimeter and length L is the length between section 1 and section 2. Okay, that is what I mentioned here. Wetted area is pi d L. Now, this equation becomes, so therefore, f1 is equal to small f1 into pi d, the perimeter, into the length between section 1 and section 2. I represent this as capital L into velocity square. Okay. Now, in this case, since we assume the fluid is a uniform flow, velocity at section 1 is equal to velocity at section 2, that is equal to velocity v. Therefore, this equation takes up the form f1 is equal to small f1 into pi d into L into v square. Okay. So, what is the thing you need to remember here? Do not put this pi d square by 4. Never ever do that. Remember, you are talking about the frictional resistance. Whenever you are talking about a frictional resistance, when the water is flowing in a pipe, this water is in contact with the entire perimeter. When I am talking about the perimeter, okay, wetted area, you need to consider this perimeter into the length between the two sections, that is 1 1 and 2 2, that we represented as capital L. So, that is the reason in place of this wetted area, I wrote this pi d L. I hope things are clear. Now, look at this. So, therefore, f1 is equal to f1. Now, pi d replaced by this perimeter and L keep it as it is and v square as it is. Therefore, the frictional resistance or the frictional force is equal to this f1 p L v square. Okay. So, you have a control volume. At one end, at section 1 you have the pressure force, at section 2 you have the pressure force. In addition to these pressure forces at both ends of the control volume, you have a frictional force opposite to the direction of flow. That is what I mentioned in the next couple of steps. The forces acting on the fluid between section 1 1 and 2 2 are the pressure force at 1 1. What is pressure force or the total pressure? Intensity of pressure into the area on which it acts. Okay. At section 1 1, the intensity of pressure is represented as P1. P1 into area on which it acts gives me the total pressure or the pressure force. Similarly, at section 2 2, it is given by the intensity of pressure at 2 into the area on which it acts. The area remains same, it is A. Therefore, the total pressure or the pressure force at 2 2 is given by P2 into A. Just now you derived an equation for this frictional force F1, that is this small f1 into perimeter into L into v square. Now, resolve these forces in the direction of flow. See what you are going to get. Resolving the forces in the direction of flow and equate the same to 0, we have this P1 into A, that is in the direction of flow, P2 into A, which is opposite to the direction of flow, that is why I put a negative sign, and the frictional resistance is always opposite to the direction of flow. So, you have A minus F1 here. So, P1A minus P2A minus F1 is equal to 0. Now, if you look at these two terms, A is common, take out this A, you are going to get this P1 minus P2 minus F1. Now, what is F1? You derived this equation F1, the frictional resistance, into the perimeter into length into V square, this must be equal to 0. Now, take out this P1 and P2 on the left hand side, push the other term, all other terms to the right hand side, you are going to get this F1 into PL V square divided by A. Now, if you kindly recall, this P1 by gamma minus P2 by gamma is nothing but your head loss. I repeat, P1 by gamma is the pressure head at section 1, P2 by gamma is the pressure head at section 2. The difference between these two will gives you the head loss due to friction, HF. Therefore, this P1 minus P2 is equal to gamma into HF. So, what I am going to do is, in this equation I am going to replace this P1 by P1 minus P2 by this gamma HF. If you do that, you are going to get this equation as gamma HF is equal to this F1 into PLV square whole thing divided by A. So, what is your aim? Your aim is to find an equation for this HF, or your aim is to find an equation for this coefficient of friction HF. Therefore, HF is equal to, so this F1 PLV square divided by A into gamma. Kindly rearrange this equation. What I am going to do is, I am going to rewrite this equation as F1 by gamma. So, here P by A into LV square. Okay. So, first let us talk about this P by A. P is perimeter pi d and A is pi d square by 4. If you substitute these values and if you simplify this, you are going to get this P by A is equal to 4D. Now, in this case, in place of this P by A, you substitute this 4 divided by D. See what you are going to get. Therefore, this HF is equal to F1 by gamma into 4LV square divided by D. Now, this is a constant F1 by gamma. Now, this F1 by gamma can be written as F divided by 2G. I am sorry. Okay. Again I repeat, this F1 by gamma can be replaced as F divided by 2G. Now, F is called the coefficient of friction. If you replace this F1 by gamma by this F by 2G, okay, then this equation takes the form HF is equal to F divided by 2G into 4LV square by D. If you simplify this, you are going to get this HF is equal to 4FLV square divided by 2GD. So, this equation is called Darcy-Weisbach equation, one of the most popular equations in fluid mechanics, especially when you are talking about friction loss in case of pipes. Okay, very simple derivation. Let us quickly look into how we derived this equation once again. So, in order to derive this equation, I consider a horizontal pipe. On this horizontal pipe, I consider two sections, section 11 and section 22. Section 11 and section 22 is separated by a distance L. We define this P1, intensity of pressure at 1, V1, velocity of flow at 1. D is the diameter of the pipe. I defined for the first time F1, small f1. Small f1 I defined as the frictional resistance per unit wetted area per unit velocity. Then we define this HF. HF is the head loss due to friction. Similarly, at section 22, we define this P2, intensity of pressure at section 22. Then we define this V2, velocity of flow at 22. Once you are defining these terms, apply Bernoulli's equation between 11 and 22. Okay. So, P1 by gamma plus V1 square by 2G plus Z1, the total energy at 11, that is equal to P2 by gamma plus V2 square by 2G plus Z2 plus HF at 22. Now, since this is a horizontal pipe, my daytime energy at section 1 is equal to daytime energy at section 2. Therefore, Z1 and Z2 gets cancel each other. I also made an assumption. What is the assumption? The flow through the pipe is uniform. So, what is uniform flow? The various physical parameters do not change along the reach. Okay. Therefore, in this case, my velocity at section 11 is equal to velocity at section 22. So, in this case, my V1 square by 2G is equal to V2 square by 2G. Therefore, you will left with this P1 by gamma is equal to P2 by gamma plus HF. Kindly rearrange this equation. I am looking for the value of HF. HF is equal to P1 by gamma minus P2 by gamma. Now, we define this frictional force, or this frictional force is equal to the frictional resistance per unit wetted area into velocity square. Frictional force is given by this formula. You need to remember this. Frictional resistance per unit wetted area into velocity square. Now, I said whenever I am talking about a wetted area, especially in case of pipes, you need to talk about, so water is flowing all along the perimeter. Therefore, wetted area is equal to perimeter into the length between section 11 and section 22 pi dl. Therefore, your frictional force is equal to F1 into pi dl into V square. Okay. So, pi d is given by perimeter, therefore, in place of pi d, if I substitute the value of P, then this frictional force is given by F1 is equal to small f1 into P into L into V square. So, what are the forces acting on the control volume? At one hand you have the pressure force, at the other hand you have the pressure force, and in between these two sections, okay, there is what is known as frictional force, which is always acting opposite to the direction of flow. You have three forces. Now, resolve these forces in the direction of flow and equate the same to 0. If you do that, you are going to get this P1A minus P2A minus F1 is equal to 0. Now, you know the value of F1, substitute the value of F1, and on simplification you are going to get this f of f is equal to F1 into P into L into V square divided by A gamma. Kindly rearrange this. So, if you rearrange this, this becomes F1 by gamma into P divided by A into L V square. Now, P is perimeter, that is given by pi d, A is equal to pi d square by 4. If you substitute that, you are going to get this P by A as 4 divided by d. Substitute this value. So, HF will take the form HF is equal to F1 by gamma into 4 LV square by 2g. At this stage, this F1 by gamma is a constant that can be written as F divided by 2g. So, if you replace this F1 by gamma by this F by 2g, and on simplification, you are going to get an equation HF is equal to 4F LV square divided by 2GD. Now, this equation is called Darcy-Weisbach equation, one of the most important equations in fluid mechanics. I hope things are clear, right? Then, sometimes they will ask you to calculate the value of F. Okay. Now, how to calculate the value? What is this F? F is a friction factor. What we determined now? We derived an equation for this friction loss, HF. Kindly recall, HF represents the loss due to friction. The question I am asking is that 4F LV square by 2GD, what is the value of F? What is this F? F is called the coefficient of friction. So, suppose if I want to calculate this F in terms of shear stress, how to do that? Okay. So, for that, the equation what we derived for this Darcy-Weisbach equation, you consider the same equation. Okay. Now, remember there are three forces acting on the control volume: the pressure force at section 1, pressure force at section 2, and the frictional resistance. Up to this, the same steps what we followed for the Darcy-Weisbach equation, the same steps you please copy, and from here afterwards, so consider this, you keep these two terms on the left hand side and push this F1 on the other side. Now, A into P1 minus P2 is equal to F1. This is force due to shear stress sigma. For the first time, here we are introducing the shear stress. Kindly recall. So, what is stress? Stress is equal to force divided by area. I repeat. So, stress is equal to force divided by area. Then in that case, what is force? Shear stress or stress into area. Now, remember, whenever you are talking about a fluid, in place of stress, we talk about what is known as shear stress. What is shear stress? One layer slides smoothly over the other layer. Okay. So, in fluid mechanics, we talk about shear stress. Okay. Therefore, F1 is equal to shear stress. Actually, that is represented by tau. I represent this as sigma, absolutely not an issue. Okay. Shear stress into surface area on which the shear stress acts. Again, so this shear stress acts all along the perimeter over a length of L. This is sigma into pi d into L. Now, look at this, you have a pi d term here. On LHS, you have this A. What is A? The cross sectional area of the pipe, pi d square divided by 4. In place of A, substitute this pi d square by 4. On the right hand side, you have this pi d. Therefore, if you substitute and simplify this, you are going to get this as d into P1 minus P2 is equal to 4 sigma L, or P1 minus P2 is equal to 4 sigma L divided by d. Okay. Now, what is this HF? Again, HF is the head loss due to friction, that is the pressure head at section 1 minus the pressure head at section 2, P1 minus gamma minus P2 by gamma. that is equal to, that is given by Darcy-Weisbach equation, 4f LV square by 2 GD. Now look at this, this P1 by P2 is given by 4 sigma L divided by D. Now in place of this P1 by P2, P1 minus P2, you substitute this 4 sigma L divided by D. Okay. So into 1 over gamma. So if you substitute this and if you simplify this, you are going to get this P1 minus P2 is equal to 4f LV square by 2 GD into gamma. Okay. Now if you simplify this, what is your aim? Your aim is to find an equation for the coefficient of friction, F. Coefficient of friction is represented as F. So you have the left hand term, you have the right hand term. So from these two terms, find the value of F. It is only a manipulation of these two equations. Okay, if you simplify these two terms, so at the end you are going to get this F is equal to 2 sigma divided by, so V square into rho. What is this rho? Rho is the mass density of the fluid flowing in the pipe. What is sigma? Sigma is the shear stress. What is V? V is the velocity of flow. Remember, we made an assumption that the flow is uniform. Again I repeat, the coefficient of friction is given by 2 times the shear stress divided by V square into rho, or rho into V square, whatever the way you feel comfortable, write that. This is how you are going to find the value of F. Once you find the value of F, so the value of HF is given by 4f LV square divided by 2 GD, right. So Darcy-Weisbach equation and how to find the value of F in terms of shear stress. I hope it is clear. Now let us solve a simple problem on this head loss due to friction. Read the problem. An oil of specific gravity 0.7 is flowing through a pipe of diameter 30 centimeter at the rate of 500 liters per second. Find the head loss due to friction and power required to maintain the flow for a length of 1000 meters. Take kinematic velocity. So Kv is kinematic viscosity, kinematic viscosity is equal to 0.29 Stokes. Again I repeat, Kv represents kinematic viscosity. If you kindly recall, in the first chapter, you under this viscosity, you studied 2 types of viscosity. One is dynamic viscosity, the other one is kinematic viscosity. Kinematic viscosity in this case is given by 0.29 Stokes, that is given in the problem. Let us see how to solve this problem. First, note down the data given in the problem. What is the data given in the problem? Specific gravity of oil is 0.7, diameter of the pipe D is 30 centimeter. Therefore, convert that into meters, 0.3 meter. Discharge 500 liters per second. I said 1 liter is equal to 1 by 1000 of a meter cube. Therefore, it is 0.5 meter cube per second. Length of the pipe between section 1 and section 2 is 1000 meters. So write that. Then velocity. So using that continuity equation, Q is equal to A into V. So let me calculate the value of velocity V. So V is equal to Q divided by E. So how you are going to calculate the value of area? Because you know the diameter of the pipe. Diameter of the pipe is 0.3. So pi d square divided by 4. Therefore calculate the value of area. Therefore velocity works out to be 7.07 meter per second. Now, in order to calculate the value of this coefficient of friction, there is another formula which is very popular in fluid flow. Kindly recall, in hydrokinematics, you studied about laminar flow, turbulent flow and transitional flow. When do you say that flow is laminar? When do you say the flow is turbulent? And when do you say the flow is transitional? In order to classify these flows into laminar, turbulent and transitional flows, we make use of what is known as this Reynolds number. Okay. If you kindly recall, if the Reynolds number is less than or equal to 2000, we call it as laminar flow. If the Reynolds number is more than 4000, okay, then we call it as turbulent flow. In between this 2000 and 4000, we call it as what is known as transitional flow. Now, this Reynolds number is given by the velocity of flow through the pipe into the dia of the pipe divided by this kinematic velocity, kinematic viscosity. Just now we calculate the value of velocity 7.07, diameter of the pipe 0.3, that is given in the problem. So, kinematic velocity is 0.29 Stokes. Okay. So, convert that into proper units, that becomes 0.29 into 10 power minus 4. If you simplify that, you are going to get the Reynolds number as 7.316 into 10 power 4. Okay. Why do you need this Reynolds number? Just now we derived an equation for this coefficient of friction in terms of shear stress. In this case, in this problem, I do not know the value of shear stress. So, whatever the data that is given in the problem, through that data I try to calculate the Reynolds number, and using this Reynolds number I try to connect the Reynolds number with the coefficient of friction. That is what I did in the next step. The relation between coefficient of friction and Reynolds number is given by 0.79 divided by Reynolds number raised to 1 by 4. This derivation is not there in the syllabus. Kindly you need to remember this formula for solving the problems. You need to remember two formulae. I hope you already studied this Reynolds number. Rn is equal to V into D divided by kinematic viscosity. But this coefficient of friction F is equal to 0.79 divided by Reynolds number raised to 1 by 4. You need to remember this formula. Now, just now we calculate the value of Reynolds number, substitute the value in this equation, and if you find the value of F, F works out to be 0.0048. That is the coefficient of friction. Now, once you know the coefficient of friction, straight away consider the Darcy-Weisbach equation. HF is equal to 4f Lv square by 2 GD and substitute the values. Let us do that. Look at this, 4f Lv square by 2 GD. Just now we calculate the value of F, substitute that value of F is equal to 4 into 0.079 into L is 1000 meters and V is 7.073 square divided by 2G constant into diameter is 0.3. Therefore, HF is equal to 163.18 meter. So, that is the loss of head in the given problem. So, next step of the problem is you are required to calculate the power. Now, you are going to study these equations probably in the next semester. Now, power required is given by gamma QH divided by 75. Remember, I am talking about metric system here. When I am talking about HP, it represents a metric system. If you talk about a SI system, then the power required is given by gamma QH. Okay. Since I am talking about HP metric system, gamma QH divided by 75, automatically it will be converted into HP, which is nothing but the horsepower. So, gamma is, so the specific gravity of fluid flowing in the pipe is given by 0.7, 0.7 into 1000, the specific weight of water in MKS system, into HF is, so just now you calculated this is 163.18 divided by 75. If you simplify this, you are going to get the power required, that is 761.50 HP. Okay. So, this is how you are going to calculate the head loss due to friction and also the coefficient of friction, and if asked, you need to calculate the power required. Okay. Now, that is about deriving an equation for this head loss due to friction. So, I'll stop at this class stage. I'll continue with this minor losses in the next class. Now, again a recall. So, pipe flow is very important for a civil engineer. So, whenever there is a fluid flowing in the pipe, there are two types of losses. One is a major loss, the other one is a minor loss. Major loss is due to friction loss, minor loss is due to so many reasons. One is loss at entrance, loss at exit, loss due to sudden expansion, loss due to sudden contraction, loss due to bends, and if there is an obstruction in the flow field, all this constitute what is known as minor loss. Now, due to these losses, there is a pressure drop from section to section. Now, we need to calculate this pressure drop, or in other words, what is the loss from section 1 to section 1, so that it will be easy for us to design the pipe systems or design a turbine or a pump, which you are going to study in the next semester. So, with that, I will stop at this stage. Thank you very much.